Proxima Centauri sits 4.24 light-years away. Write that number out in kilometers, and you get roughly 40 trillion. 40 followed by 12 zeros. The fastest spacecraft humans have ever launched, the Helios probes of the 1970s, reached speeds of about 242,000 kilometers per hour. At that pace, the journey to Proxima Centauri would take about 19,000 years. 19,000 years ago, humans were painting cave walls at Lascaux. Agriculture hadn't been invented. Writing was 20,000 years in the future. The entire span of recorded human civilization fits comfortably inside half that travel time. And the Helios probes weren't going anywhere near Proxima Centauri. They were orbiting the Sun. Getting to another star requires not just speed, but sustained speed. And nothing humans have built even approaches what that would require. The problem starts with physics and never gets better.
To reach Proxima Centauri in a human lifetime, say in 100 years, a spacecraft would need to travel at roughly 4% of the speed of light. That's about 43 million kilometers per hour. For context, the New Horizons probe, which flew past Pluto in 2015 and remains one of the fastest objects humans have ever launched, travels at about 58,000 kilometers per hour. The required speed is about 740 times faster than New Horizons. Reaching 4% of the speed of light isn't just an engineering challenge, it's an energy challenge of a different order entirely. The kinetic energy required to accelerate a spacecraft of modest mass, say 1,000 kilograms, roughly the mass of a small car, to 4% of the speed of light is approximately 2 × 10⁻17 joules. That's equivalent to roughly 5 million Hiroshima bombs per 1,000 kilograms of spacecraft. A crewed vessel capable of sustaining human life for decades would weigh orders of magnitude more. The energy requirements scale proportionally. No energy source humans currently possess, or can plausibly develop within any near-term time frame, comes close to providing that output. Rocket propulsion, the technology that got humans to the moon, fails completely at interstellar scales. Chemical rockets work by burning propellant. The exhaust velocity of chemical propellants, the speed at which gas exits the nozzle, tops out around 4 to 5 kilometers per second. The spacecraft's maximum achievable velocity depends critically on the ratio of propellant mass to final mass, described by the Tsiolkovsky rocket equation. At 4% of light speed, about 12,000 kilometers per second, a chemical rocket would need a mass ratio of propellant to final spacecraft mass of approximately 10 to the power of 1,000. Not 10 to the power of 10, 10 to the power of 1,000. A number with 1,000 zeros. There isn't enough matter in the observable universe to build that rocket. Ion drives improve efficiency dramatically. The specific impulse, a measure of propellant efficiency, of ion drives runs roughly 20 times higher than chemical rockets. Still not close. Nuclear thermal propulsion, studied seriously by NASA in the 1960s under Project Nerva, could reach specific impulses of 800 to 900 seconds, offering perhaps twice the efficiency of the best chemical propellants. Still nowhere near interstellar requirements. The only propulsion concepts that come close involve physics that either doesn't exist or can't be practically implemented. Nuclear pulse propulsion, the Orion concept, proposed using nuclear bomb detonations behind a spacecraft to push it forward. A serious study by Freeman Dyson in the 1950s and 1960s suggested that a large Orion vehicle could potentially reach several percent of light speed. The concept works physically, but it requires detonating thousands of nuclear bombs in rapid succession behind a crewed spacecraft, violates multiple international treaties, and would need a vehicle massing millions of tons. Fusion propulsion theoretically offers exhaust velocities approaching several percent of light speed. The problem? Humanity has been attempting to achieve sustained, controlled nuclear fusion for about 70 years, and as of the mid-2020s, it remains a research challenge without a commercially operational fusion reactor. Fusion propulsion for interstellar flight requires not merely functional fusion,
but fusion at specific fuel combinations, ideally hydrogen-boron or helium-3 reactions that remain far beyond current capability.
The Bussard ramjet, proposed by Robert Bussard in 1960, imagined scooping interstellar hydrogen with a magnetic funnel and using it as fuel. Elegant in concept, fatally flawed in physics. The interstellar medium is too sparse. The drag from the magnetic funnel would likely exceed the thrust generated, and the required magnetic fields would be enormous. Calculations in the decades after Bussard's proposal consistently showed the concept doesn't work as described. Laser-driven light sails, currently the most seriously pursued interstellar concept, embodied in breakthrough starshot, propose accelerating gram-scale wafers to 20% of light speed using a ground-based laser array delivering 100 gigawatts of power. The physics doesn't violate anything fundamental, but the engineering challenges are profound. The laser array doesn't exist. The sails must survive enormous thermal stress during the acceleration phase. The wafers must carry cameras and communications equipment while massing only a fraction of a gram. And they can't decelerate at the destination. They would fly past Proxima Centauri in hours. Breakthrough Starshot targets Proxima Centauri with probes, not humans. Crewed missions don't enter the calculation. Time itself becomes an adversary at the distances involved. Even at 4% of light speed, an achievement that would require energy sources and propulsion technologies far beyond anything currently operational. A journey to Proxima Centauri takes 100 years. Human lifespans don't stretch that far for most people. A mission launched with a 30-year-old crew would arrive, if it arrived, with a crew of 130. More likely, it would arrive crewless, or with generations of crew born and died en route. Generational ships. Vessels designed to house multiple generations of crew members over a century or more of travel appear in science fiction as a solution. But they reintroduce the problem from a different angle. A vessel capable of sustaining a genetically viable human population, typically estimated to require a minimum of a few hundred to a few thousand individuals for genetic diversity, for 100 years would need to be enormous. The food production systems, the waste recycling, the medical facilities, the psychological support systems, the governance structures necessary to prevent social collapse over multiple generations, each adds mass, complexity, and failure modes. Such a vessel would need to be essentially a self-sustaining civilization in a can, traveling through absolute vacuum with no possibility of resupply, repair from outside, or rescue. Radiation poses a specific threat that engineering cannot fully solve. The interstellar medium outside the solar system offers no protection from galactic cosmic rays, high-energy particles produced by distant supernovae and other violent processes, traveling at near light speed and arriving from all directions. The Sun's magnetic field, the heliosphere, deflects many of these particles. Beyond the heliopause, roughly 120 astronomical units from the Sun, that protection ends. Galactic cosmic rays include heavy ions with enormous energies per particle. They penetrate essentially any reasonable shielding. The secondary particles produced when primary cosmic rays interact with shielding material can be as damaging as the primaries. Water, polyethylene, and other hydrogen-rich materials offer the best shielding per unit mass, but the mass required to provide meaningful protection over decades of exposure is prohibitive. NASA's Human Research Program has studied the radiation environment extensively in the context of Mars missions. A journey measured in months, not years or decades. The cumulative radiation dose from a Mars mission already approaches career limits for astronauts. A journey of decades would deliver doses far exceeding anything within safe limits by current understanding. The physics of radiation interaction with tissue doesn't offer a clear engineering workaround. You can reduce exposure somewhat with shielding. You can't reduce it to safe levels for a journey of 100 years without either physics breakthroughs in active shielding using magnetic fields, which consume enormous power and add enormous mass, or some biological solution that doesn't currently exist.
The psychological dimension receives less attention than the physics, but it may be equally decisive. In 2019, and continuing into 2023, NASA commissioned extensive studies of long-duration space mission psychology. The most isolated analog environments humans have studied, Antarctic winter overstations, nuclear submarines on extended patrols, analog habitats like HISEAS in Hawaii, consistently show that prolonged confinement with a small, fixed group produces predictable psychological deterioration. Conflict, depression, cognitive decline, loss of motivation, breakdown of social cohesion. The longest continuous human spaceflight records run to about 438 days, the record set by Valery Polyakov on Mir in 1994 to 1995. Even at 4% of light speed, the journey to Proxima Centauri lasts roughly 100 years. That's not a duration humans have ever attempted to sustain in isolation. It's not a duration for which any psychological preparation protocol exists. The crew of a generation ship would spend their entire lives, from birth to death, inside the vessel. They would never experience planetary gravity, wide open spaces, the presence of more than a few hundred other human beings, or any environment other than the interior of the ship. The psychological effects of that existence on a human population over multiple generations remain genuinely unknown. There are no analogues. No experiment that approximates it has ever been run. Communication across interstellar distances breaks in ways that seem simple but cut deep. Light takes 4.24 years to travel from Earth to Proxima Centauri. A signal sent from the spacecraft takes the same time to arrive at Earth, and any response takes the same time to return. A conversation, a simple question and answer, requires a minimum of 8.48 years round trip. For a mission launched in the mid-21st century, the ground crew communicating with the vessel would be dead before receiving replies to questions sent years into the mission. The crew's children's ground contacts would be dead. By the time the vessel arrived at Proxima Centauri, the civilization that launched it would be unrecognizably transformed, politically, culturally, technologically. What obligations does a civilization have to a crew it launched 100 years prior? What authority structures survive across a century of communication delays? What if the civilization on Earth decides, 50 years into the mission, that the goals have changed, that the mission is no longer worth supporting, or that the destination is no longer of interest? These questions have no precedent in human institutional history. Every previous long-duration human expedition has maintained the possibility of communication, resupply, or rescue within reasonable timeframes. Interstellar missions eliminate all three. Deceleration, the problem nobody talks about enough. Getting to 4% of light speed requires enormous energy. Slowing down at the destination requires essentially the same energy again. A spacecraft hurtling through the Proxima Centauri system at 43 million kilometers per hour would pass through it in a matter of hours without deceleration capability. Useful exploration of the system requires stopping, or at least slowing dramatically. Nuclear pulse propulsion concepts require carrying both the propellant for acceleration and the propellant for deceleration, roughly doubling the already astronomical fuel mass requirements. Laser-driven light sails can be accelerated by pushing from behind, but decelerating requires something at the destination, a laser array that doesn't exist, to push from the front. Magnetic braking using the stellar wind of Proxima Centauri has been proposed, but the required magnetic fields and the interaction physics remain deeply uncertain. Robert Forward, who spent decades thinking seriously about interstellar propulsion, proposed a staged laser sail system, where part of the sail detaches and reflects the laser back at the remainder to decelerate it. The engineering complexity is extraordinary. Nothing resembling it has ever been built or tested. The most honest assessment of alternatives. Cryogenic hibernation, freezing crew members for the journey, appears in science fiction as the obvious solution. The biology doesn't currently support it. Humans cannot be frozen and revived.
The ice crystals formed during freezing rupture cell membranes. Cryoprotectants can reduce ice formation at small scales, and there's active research into suspended animation using hydrogen sulfide and other approaches that have worked in some animal models. As of the mid-2020s, no human has ever been successfully placed in long-term cryogenic suspension and revived. The gap between research progress and interstellar mission requirements is enormous. Even optimistic projections from researchers in the field don't place practical human cryogenic suspension within the same century as a plausible interstellar mission. Artificial intelligence autonomous probes without human crew sidestep the biological problems entirely. But they aren't human presence at another star. They represent an extension of robotic exploration, enormously valuable scientifically, but not the same thing as humans reaching another star system. Generation ships avoid cryogenics but introduce the multi-generational psychological and genetic problems described above. No middle ground currently exists. The economics deserve a frank statement. Breakthrough Starshot, the most credibly funded serious interstellar initiative as of the mid-2020s, has a stated budget of $100 million for the research phase. The full mission, if ever built, would cost orders of magnitude more. Estimates for a functional laser array of the required scale run to tens of billions of dollars. For a crewed mission, the scale comparison becomes almost meaningless. The International Space Station cost approximately $150 billion to build and operate through the early 2020s. A crewed interstellar mission would require energy sources, propulsion systems, life support for decades, radiation shielding, and communication infrastructure, each of which individually dwarfs ISS costs, combined into a single mission. No government or private entity has ever funded a project of remotely comparable scale. The Apollo program, at its peak, consumed about 4% of the US federal budget. A crewed interstellar mission would require a sustained commitment of comparable or greater magnitude for decades from an institution that doesn't yet exist in the global political landscape. The economics aren't incidental to the question. They're central to it. Even if every engineering challenge were solved, the project would require political and economic coordination across generations that has no historical parallel outside of wartime mobilization. What never means and doesn't mean. The title says never. That word deserves careful treatment. Never in the next century. Almost certainly true. No credible technical roadmap places crewed interstellar flight within 100 years. The propulsion physics alone require breakthroughs that don't have clear development paths. Fusion power, potentially a prerequisite, remains decades away from commercial operation. Never in the next 1,000 years. Plausible, depending on assumptions about technological development. 1,000 years is a long time. 1,000 years ago, humans had no concept of heavier-than-air flight, no understanding of electromagnetism, no mathematics capable of describing quantum mechanics. Projecting 1,000 years into the future with confidence in either direction, will or won't, reflects more about psychology than about physics. Never, as in forbidden by the laws of physics, false. Nothing in known physics prevents humans from traveling to Proxima Centauri. Relativity permits it. The energy requirements are enormous but finite. The distances are vast but not infinite. The statement isn't, "It violates physics." The statement is, the gap between what the physics requires and what humans have ever built is so large that no credible timeline for closing it exists. That's different from impossible. It's more like so difficult that discussing it in human lifetime terms misrepresents the scale of what would be required. The nearest star already tells us something, without our going there. Proxima Centauri hosts at least 2 confirmed planets. Proxima b, discovered in 2016, orbits in the habitable zone, the range of distances where liquid water could exist on a planetary surface. Proxima d, announced in 2022, orbits much closer to the star and receives intense radiation.
The system receives intense ultraviolet and X-ray radiation from its host star's frequent flares. Whether Proxima b is habitable in any meaningful sense remains unknown. Whether it has an atmosphere, water, or any conditions supporting life, unknown. The James Webb Space Telescope, in principle capable of atmospheric characterization of nearby exoplanets through transit spectroscopy, faces significant challenges with Proxima b because Proxima Centauri is a flare star whose activity complicates measurements. We can study Proxima Centauri and its planets at a distance. We can infer things about them. We cannot visit them within any time frame that the word plan meaningfully applies to.
The nearest star sits 4.24 light-years away and might host a habitable world. Humans will not reach it within any planning horizon that means anything to any person alive today. The speed of light feels like a wall. It isn't technically. Relativity permits travel at any fraction of light speed, and nothing in the equations says a spacecraft cannot reach 99% of c given sufficient energy. But the energy requirement at high fractions of light speed grows in a way that makes the wall metaphor feel accurate. At 10% of light speed, the kinetic energy of a 1,000 kilogram spacecraft is roughly 4.5 times 10 to the 18th joules. At 90% of light speed, accounting for relativistic mass increase, the energy required for the same mass exceeds 10 to the 20 joules by a significant margin. The relativistic factor, gamma, begins compounding against you. At 99% of light speed, gamma equals approximately 7. At 99.9%, it exceeds 22. Fuel requirements scale with gamma in ways that make already impossible numbers become cosmically absurd. This matters because the only circumstance under which interstellar travel becomes remotely plausible for humans involves high fractions of light speed, not to beat the energy problem, but to exploit time dilation. Relativistic time dilation compresses subjective travel time for the crew, while objective time passes normally on Earth. At 99% of light speed, gamma equals approximately 7. So what feels like 14 years of travel to the crew corresponds to 100 years on Earth. At 99.9%, the crew experiences roughly 4.5 years, while Earth ages 100 years. Proxima Centauri in a human lifetime becomes conceivable only if you're willing to accept that the civilization you return to, if you return, has aged a century or more, while you experienced a few years. And to reach those speeds, you need energy that doesn't exist in any practical form accessible to humans. The thermal problem compounds everything. Any spacecraft traveling at a significant fraction of light speed must push through the interstellar medium. Not quite a vacuum, but close enough that it sounds like one. The interstellar medium contains roughly 1 hydrogen atom per cubic centimeter on average, plus trace amounts of dust and larger grains. At 1% of light speed, the relative velocity of incoming hydrogen atoms is 3,000 kilometers per second. At those velocities, hydrogen atoms carry kinetic energies comparable to heavy ions in a particle accelerator. They're no longer innocent drifting atoms. They're high-energy projectiles, and anything they strike is effectively being bombarded by a stream of cosmic rays created by the spacecraft's own motion. At 10% of light speed, the bombardment intensity increases by a factor of roughly 100 relative to the 1% case, because the energy scales as the square of velocity and the flux scales with velocity. The leading face of any interstellar spacecraft would be eroded at a rate that depends on material properties, but estimates suggest erosion becomes severe enough to destroy conventional materials within years or decades at these speeds. Shielding helps. A cloud of hydrogen gas or a block of ice ahead of the spacecraft could absorb bombardment, but the shield itself erodes, requires replacement or replenishment mechanisms that don't exist, and adds mass to an already constrained mass budget. Active electromagnetic deflection, using magnetic fields to sweep ionized particles away from the spacecraft's path, could in principle handle protons, but neutral hydrogen atoms remain unaffected by magnetic fields.
The dust problem is potentially more dangerous than the gas problem. Interstellar dust grains vary in size from nanometers to micrometers. A single dust grain of 1 micrometer diameter, struck at 10% of light speed, delivers a kinetic energy equivalent to a small explosive. At 20% of light speed, breakthrough starshot's target velocity, the energy per gram of impacting material is roughly 6 gigajoules. A dust grain massing 1 microgram delivers 6,000 joules, comparable to a rifle round. The statistical frequency of dust grain impacts over 4 light-years of travel remains uncertain because the dust distribution in the interstellar medium is not perfectly mapped. Estimates suggest potentially thousands of damaging impacts per square meter of frontal area over an interstellar journey. For gram-scale probes, this might be manageable through redundancy and nanoscale design. For a crewed vessel, with frontal area measured in hundreds of square meters, it's a catastrophic attrition problem. The navigation challenge at interstellar speeds has no current solution. At 4% of light speed, the minimum plausible for a century-scale journey, a spacecraft travels about 43,000 kilometers per second. At that speed, a navigation error of 1 degree off course accumulates to roughly 15 billion kilometers of positional error over 4 light years. The spacecraft would miss the Proxima Centauri system entirely. Correcting course requires knowing where you are, knowing where you need to be, and having propulsion capacity to execute the correction. Star trackers, instruments that determine orientation relative to known star positions, work well in the inner solar system and have been used reliably for decades. At interstellar distances, the stellar background appears slightly different due to parallax shifts, complicating the reference frame. Mid-course corrections require propulsion. Every kilogram of propellant dedicated to course corrections is a kilogram not available for deceleration. Deceleration propellant is already the most mass-constrained item in the mission. Navigation errors that require significant correction could compromise the entire mission. For robotic probes, navigation tolerances might be relaxed somewhat. Flying through the Proxima Centauri system at high speed and imaging the planets would still return useful data. For a crewed mission requiring actual orbital insertion around Proxima b, navigation tolerances become extremely tight, and the propulsion budget for corrections becomes critical.
The communication delay compounds navigation problems. If ground controllers notice from telemetry that the spacecraft is off course, a correction signal takes 4 years to arrive. The spacecraft has been on the wrong heading for 4 years by the time the correction command arrives. Autonomous navigation algorithms would need to handle this without ground input, requiring computational systems capable of reliable, autonomous decision-making over decades, which represents a significant software engineering challenge with no current parallel. The closest analog to an interstellar mission, and what it actually teaches. The Omega and HI-Cs experiments placed small groups of humans in isolated habitats for periods ranging from 4 months to 1 year, simulating the psychological environment of a long-duration space mission. The most closely studied real-world analog remains the Russian Antarctic Winter Over program at Vostok Station, where small groups of researchers have spent a year or more in extreme isolation since the 1950s. From decades of these studies, psychologists have identified a cluster of phenomena that appear reliably in isolated groups. The third quarter phenomenon, a measurable deterioration in mood and performance roughly 3/4 of the way through a known mission duration. Interpersonal conflict that begins minor and escalates. Cognitive narrowing, a gradual reduction in the breadth and flexibility of thinking. A pattern psychologists call expeditionary behavior that varies significantly between individuals and predicts mission success better than almost any pre-mission screening metric. The HISEAS studies at Mauna Loa, Hawaii, showed that even in a simulation with the knowledge that ground contact and extraction were available, groups of 6 showed measurable conflict escalation over 8-month missions. The researchers could end the simulation and walk outside. Crew members on an interstellar vessel cannot. No analog study has run longer than about 14 months of continuous isolation. An interstellar mission requires psychological stability, not just survival, but productive functioning, over timescales 100 times longer, in a crew that can never be extracted, resupplied, or reinforced. The database of knowledge about human behavior in such circumstances contains literally no data points. Genetic viability over multiple generations adds another layer of difficulty. Population genetics places constraints on the minimum viable population needed to maintain genetic diversity over multiple generations without significant inbreeding depression. The estimates vary by methodology and assumptions, but commonly cited figures for a multi-generational space mission range from a few hundred to several thousand individuals. Cameron Smith of Portland State University published work in 2014 estimating that a minimum crew of around 40,000 would be needed for a multi-generational mission to Proxima Centauri of sufficient duration to allow intermediate generations. Smith's calculation accounts for random genetic drift, the risk of disease decimating a small population, and the genetic bottleneck effects of prolonged isolation. 40,000 people on a single vessel, sustained for 100 years, represents a construction and life support challenge beyond anything in human engineering history. More recent analyses have suggested somewhat lower numbers are plausible with careful genetic management, sperm and egg banking, embryo storage, deliberate pairing strategies. But even the lower estimates, in the range of a few hundred genetically diverse individuals, produce a vessel that must support a population with medical facilities, food production, recreation, education, governance, and social organization for a century. The social engineering problem may exceed the mechanical engineering problem. Human societies of a few hundred to a few thousand people in Earth-based contexts develop persistent conflicts, hierarchies, in-groups and out-groups, and governance crises. These societies have always had the option of exit. Disaffected members could leave. On an interstellar vessel, exit doesn't exist. The entire concept of opting out of a society disappears when the society occupies a sealed metal tube in interstellar space. What happens when something breaks? And something always breaks. The Space Shuttle fleet flew 135 missions between 1981 and 2011. 2 of them ended in catastrophic loss of crew, Challenger in 1986 and Columbia in 2003. That's a mission failure rate of 1.5%. Applied to a century-long interstellar mission, a 1.5% failure rate per year translates to near certain catastrophic failure before reaching the destination. The Apollo 13 mission in 1970 survived a catastrophic oxygen tank explosion through a combination of crew ingenuity, ground support from thousands of engineers working around the clock, and significant good fortune. The crew returned to Earth in approximately 4 days from the moment of failure. An interstellar vessel experiencing a comparable failure would have no ground support, only the crew on board, and no possibility of return within any timescale relevant to survival. Reliability engineering for century-scale missions requires achieving failure rates orders of magnitude lower than anything humans have built. A life support system that fails once per million operating hours sounds impressive. Over a century of continuous operation, it fails roughly once every 114 years, almost certainly during the mission. Multiple redundant systems help, but every redundant system adds mass, complexity, and its own failure modes. Perfect systems don't exist. Zero maintenance systems don't exist. The Voyager probes have operated for over 47 years as of the mid-2020s, an impressive record for an unmanned spacecraft. But they've required maintenance from the ground, they carry no life support systems, and their operating environment is far less demanding than an interstellar vessel maintaining human habitable conditions for a century. The political continuity problem, a dimension most technical analyses ignore entirely. An interstellar mission represents a commitment not just from the people who launch it, but from all subsequent governments and institutions that must sustain it. A mission launched in 2050 would arrive at Proxima Centauri around 2015. The entities that exist in 2015 bear no meaningful institutional relationship to those that would launch in 2050. Consider the institutions that existed in 1924, a century before the mid-2020s. The Soviet Union was 2 years old and would not survive to 2024. The British Empire controlled a quarter of Earth's land surface and would cease to exist in recognizable form within decades. The United States had 48 states and a population of 114 million. The United Nations didn't exist. NASA didn't exist. Most current nation-states didn't exist in their current form. The institution required to sustain an interstellar mission, providing funding, communication, mission control, and institutional purpose, must persist and maintain its commitment for a century while undergoing transformations comparable to those of the last century. No human institution has ever sustained a single project goal across 100 years without fundamental transformation of its nature, purpose, or continuity. The Roman Empire lasted centuries as a recognizable entity, but transformed profoundly throughout. The Catholic Church has institutional continuity across millennia, but has changed substantially in that time. Neither provides a model for maintaining the operational specificity required by an interstellar mission. The precise technical knowledge, the specialized personnel, the ongoing financial commitment, the unwavering commitment to a goal set a century earlier by people now dead. The destination problem: what we'd find and whether it matters. Proxima b sits in the habitable zone of Proxima Centauri, but habitable zone means only that liquid water could exist on the surface at some combination of atmospheric pressure and temperature. It doesn't mean habitable in any richer sense. Proxima Centauri emits roughly 200 times more ultraviolet radiation than the Sun during its frequent flares. Proxima b is likely tidally locked, one face perpetually pointed at the star, the other in permanent darkness. The star flares regularly enough that the planet's day side may receive sterilizing ultraviolet doses multiple times per year. If Proxima b has a substantial atmosphere that redistributes heat and filters ultraviolet, conditions on the surface could be hospitable. If it doesn't, if flares have stripped the atmosphere over billions of years, as some models suggest, the surface would be barren and irradiated. We don't know. The tools to determine this are being built, but the measurements face significant technical challenges. The reason this matters for interstellar mission planning: the destination could be uninhabitable. The mission could arrive at Proxima Centauri after 100 years of travel to find a sterile, airless, radiation-blasted world with no scientific return beyond what robotic probes could achieve, and no possibility of human settlement. The entire justification for crewed interstellar flight, as opposed to robotic exploration, usually rests on the premise that humans can do science, exploration, and potentially settlement that robots cannot. But if the destination turns out to be uninhabitable, the crewed mission offers no advantage over a probe fraction of its mass, cost, and complexity. The argument that physics will improve, and why it should be taken seriously but not too seriously. The history of technology contains genuine surprises. Heavier-than-air flight was dismissed as physically impossible by credible scientists in the early 20th century and achieved within years of those dismissals. Nuclear fission wasn't understood until the 1930s and transformed the energy landscape within a decade. Transistors, lasers, the internet, each appeared on timescales shorter than predictions of their impossibility. Some physicists and engineers argue that interstellar travel will follow a similar pattern. The current barriers look insurmountable only because we haven't yet found the right approach. Exotic propulsion concepts, Alcubierre warp drives, traversable wormholes, Mach effect thrusters, appear in the scientific literature as serious, if highly speculative, proposals. Harold White at NASA's Johnson Space Center ran serious experiments in the 2010s attempting to measure signatures of a warp bubble in laboratory conditions. The Alcubierre metric, described by Miguel Alcubierre in 1994,
provides a mathematical solution to Einstein's equations in which a spacecraft sits in a bubble of flat space while the space itself warps around it, potentially allowing faster-than-light apparent travel without violating local causality. The problem? The solution requires negative energy density, exotic matter, that has never been observed and may not exist in the amounts required. Estimates of the exotic matter needed for an Alcubierre drive have ranged from Jupiter's mass to, in more optimistic analyses, several hundred kilograms. The physics remains deeply speculative. The important distinction: chemical rocket propulsion failing to meet interstellar requirements isn't a historical precedent for a paradigm shift making interstellar flight easy. It's a case where we understand exactly why chemical rockets fall short, and no obvious paradigm exists that would change the energy and distance arithmetic.
The Wright brothers' moment happened because heavier-than-air flight was actually possible within known physics. The barriers were engineering, not physics. Interstellar travel faces barriers that are, at their core, physics. The distances are real, the energy requirements follow from conservation laws, and the speed of light is a genuine constraint. The most honest framing of the situation: humans will not reach Proxima Centauri in the next 100 years with any technology that currently exists or has a credible development path. That statement rests on physics, engineering, biology, psychology, economics, and political science, not pessimism. The statement might be wrong about the next 200 years, or 300. The uncertainty grows with the timescale. Nobody alive today can reliably predict what energy sources or propulsion technologies will be available in 300 years. The honest answer to will humans ever reach the nearest star is not no, but not with anything we currently understand how to build, and not within any time frame that's meaningful to anyone currently alive. That's a different thing from impossible. It's more like the problem is so much larger than our current capabilities that talking about it in decades is a category error. The nearest star sits 4.24 light-years away. The fastest thing humans have ever built reaches it in about 19,000 years. Closing that gap to something like a century requires improving by a factor of about 190. Each factor of 10 in improvement requires either energy sources that don't exist or physics that hasn't been discovered. The gap compounds. And yet people keep thinking about it seriously. And that's not delusional. Breakthrough starshot exists. Serious physicists write peer-reviewed papers about interstellar propulsion. Universities run departments studying long-duration spaceflight psychology. The problem is real enough to take seriously. The barriers are real enough to be honest about. The nearest star isn't going anywhere. It'll be 4.24 light-years away in 1,000 years. Whether that distance ever becomes traversable by humans depends on whether the species persists long enough and develops the physics, the technology, and the institutional capacity to close a gap that currently looks, from where we stand, effectively infinite. The speed of sound once felt like a permanent wall. In the 1940s, engineers at NACA, the predecessor to NASA, believed seriously that a shock wave would form around an aircraft approaching the speed of sound and create a barrier the aircraft couldn't penetrate. They called it the sound barrier. It wasn't a metaphor. The shock wave imposed real structural loads that destroyed early experimental aircraft before they could reach Mach 1. Chuck Yeager broke through it on October 14, 1947, in the Bell X-1, and the barrier turned out to be an engineering problem rather than a physical limit. People invoke that story constantly when discussing interstellar travel. The implication? The barriers that look permanent often aren't. What looks like a wall today may be an engineering problem tomorrow. The comparison breaks down immediately on inspection. The sound barrier was never a theoretical limit. Physics never said aircraft couldn't exceed Mach 1, only that existing materials and designs couldn't handle the transition. The speed of light is a genuine theoretical limit on the speed of matter with mass.
Chuck Yeager didn't challenge the laws of physics. He challenged the limits of then-current materials and aerodynamics. An interstellar mission challenges the laws of thermodynamics, conservation of energy, and the structure of space-time. These aren't equivalent situations.
The more useful historical comparison might be the dream of human flight itself, which took roughly 2,000 years from Daedalus to Kitty Hawk, not because of intellectual failure, but because the prerequisite technologies, lightweight materials, internal combustion engines, understanding of aerodynamics, took that long to develop. Interstellar travel may require prerequisite technologies that take comparably long to develop, or longer, or may require physics that hasn't been discovered. The sound barrier analogy flatters the problem. The mass ratio tyranny, why rockets get exponentially harder as ambitions scale. The Tsiolkovsky rocket equation, derived in 1903, states a relationship between a rocket's exhaust velocity, its mass ratio, initial mass divided by final mass, and the velocity change it can achieve. The relationship is exponential. Double the required velocity change, and the required mass ratio doesn't double, it squares. To achieve 1% of light speed with a fusion drive achieving an exhaust velocity of about 3% of light speed, an optimistic assumption for near-future fusion propulsion, the mass ratio would need to be roughly 2. A spacecraft with 1 kilogram of final mass would need 2 kilograms total, including propellant. That's achievable. At 5% of light speed with the same exhaust velocity, the mass ratio exceeds 300. 300 kilograms of propellant for every kilogram of final spacecraft. Challenging, but not insane. At 20% of light speed, the mass ratio exceeds 3 million. 3 million kilograms of propellant per kilogram of payload. An entire crewed spacecraft with life support, food production, radiation shielding, and crew might mass 100,000 kilograms. The propellant required? 300 billion kilograms. That's roughly the mass of a small asteroid. At 50% of light speed, the propellant requirement exceeds the mass of several large asteroids per kilogram of payload. The numbers stop meaning anything to human intuition. They just grow. This is why proposed high-speed interstellar concepts must either use propellant that isn't carried on the spacecraft, laser-driven light sails, or Bussard ramjets if they worked, or operate at very modest fractions of light speed and accept journey times of centuries, or require propellant mass that doesn't exist in any practical form. The Daedalus and Icarus projects, what serious engineering analysis actually found. In the 1970s, the British Interplanetary Society undertook Project Daedalus, a 5-year engineering study of an interstellar probe, not a crewed mission. The target was Barnard's star, about 6 light-years away, and the goal was a one-way flyby mission arriving within 50 years of launch. The Daedalus design used pulsed inertial confinement fusion, detonating small pellets of helium-3 and deuterium 50 times per second to produce thrust. The final design required approximately 50,000 metric tons of helium-3 as fuel, more than 3 times the amount of helium-3 estimated to exist in Earth's atmosphere. The designers proposed mining helium-3 from Jupiter's atmosphere using robotic extraction systems. The spacecraft reached a design velocity of about 12% of light speed, achieving a flyby of Barnard's star in roughly 50 years. It carried no crew. It carried no deceleration propellant. It couldn't stop. It flew through the target system at 12% of light speed, and its instruments had a few hours to collect data before it continued past. Project Icarus, a follow-on study in the 2000s and 2010s, attempted to improve on Daedalus with additional decades of fusion research. The conclusions were similar: enormous fuel requirements, heroic manufacturing challenges, and fundamental limitations on achievable mission profiles. The Icarus team identified approximately 200 significant technical challenges, each individually complex, collectively daunting. Both projects were undertaken by serious engineers applying serious analysis. Neither found a path to crewed interstellar flight.
Both found that even unmanned flyby missions to nearby stars required technologies decades beyond what currently existed. The helium-3 problem: why fuel scarcity matters even for theoretical missions. Fusion propulsion concepts frequently require helium-3 as fuel, either alone or in combination with deuterium. Helium-3 produces fewer neutrons than deuterium-deuterium fusion, making it cleaner and potentially more practical for spacecraft use. Its energy density per unit mass exceeds chemical propellants by 7 orders of magnitude. Earth contains almost no helium-3.
The total amount in Earth's atmosphere is estimated at roughly 1,500 metric tons, enough for laboratory research and some commercial applications, nowhere near enough to fuel an interstellar mission. The Moon's regolith contains helium-3 deposited by the solar wind over billions of years, in concentrations of roughly 10 parts per billion by weight. Total helium-3 on the Moon might be around 1 million metric tons, a significant resource for lunar energy production, but still far short of Daedalus scale requirements. Jupiter and Saturn contain vastly more. The atmosphere of Jupiter alone might contain several trillion tons of helium-3. Extracting it from Jupiter's powerful gravitational field and dense, turbulent atmosphere involves technologies that don't exist. Atmospheric mining platforms operating in a gas giant environment, enormous tanker vessels capable of leaving Jupiter's gravity well with millions of tons of extracted helium-3, and decades of sustained extraction operations before a single interstellar mission could launch. The helium-3 problem illustrates a pattern that appears throughout interstellar mission planning. Each solution to one problem creates several new problems of comparable or greater difficulty. Fusion propulsion solves the energy density problem. Fusion propulsion requires helium-3. Helium-3 extraction from gas giants solves the helium-3 problem. Gas giant extraction requires technologies and infrastructure that don't exist and would take decades to develop. Each step back along the dependency chain reveals another multi-decade engineering project. The biological clock: what spaceflight does to human bodies over time. Studies of astronauts returning from long-duration missions on the International Space Station have documented a catalogue of physiological effects from microgravity and the space environment. Bone density loss proceeds at roughly 1 to 2% per month in microgravity, stabilizing but not eliminating after extended exposure. Muscle mass decreases similarly. The cardiovascular system deconditions. The heart becomes more spherical and less efficient at pumping blood. Fluid shifts toward the head, produce intracranial pressure changes that can impair vision through a syndrome called Spaceflight-Associated Neuroocular Syndrome, or SANS. The twin study of Scott and Mark Kelly, Scott spending a year aboard the International Space Station while Mark remained on Earth, documented changes in gene expression, cognitive performance, microbiome composition, and telomere length over the course of a year. Most changes partially or fully reversed after Scott returned to Earth. But the key phrase is returned to Earth. The recovery depended on returning to Earth's gravity, Earth's atmospheric pressure, Earth's radiation environment. Astronauts on an interstellar mission don't return to Earth. Their exposure to microgravity and elevated radiation continues indefinitely. The long-term effects of decades of microgravity on human physiology remain genuinely unknown. No human has ever spent more than about 14 consecutive months in microgravity. Scott Kelly's year-long mission was specifically designed as a step toward understanding longer duration effects, and it still represents only a small fraction of the duration of any plausible interstellar mission. Artificial gravity through rotation could mitigate microgravity effects. A rotating habitat providing 1 g of centripetal acceleration at the outer rim requires a radius of roughly 225 meters for a rotation rate of 2 revolutions per minute, slow enough to avoid the vestibular effects of higher rotation rates. A habitat of that scale adds dramatically to the mass, complexity, and construction challenge of an already enormous vessel. The supply chain problem: What happens when something runs out? A closed-loop life support system must recycle water, air, and nutrients indefinitely with zero external resupply. The International Space Station achieves approximately 93% water recycling, recovering moisture from breath, sweat, and urine through multiple filtering and purification stages. The remaining 7% requires resupply from Earth. 7% water loss per cycle might sound manageable. Over a century with no resupply possible, even tiny inefficiencies accumulate into existential shortages. An interstellar vessel must achieve recycling efficiencies across all 100% across all critical resources, not for a year or a decade, but for a century. The International Space Station's life support systems require regular maintenance, replacement of filter elements, and periodic delivery of replacement components from Earth. A resupply mission to the ISS takes roughly 2 days from launch to docking. For an interstellar vessel, resupply doesn't exist. Every component that degrades or fails must either be repaired with materials available on the vessel or replaced from onboard spares. Food production adds another layer. Caloric requirements for a crew of several hundred over 100 years represent an enormous agricultural operation. Controlled environment agriculture systems exist on Earth, but the most efficient known crop systems, optimized leafy greens, legumes, grains, achieve caloric densities that require substantial growing area per person. Estimates for minimal crude agriculture suggest roughly 50 square meters of growing space per person for basic caloric needs, not accounting for the full variety needed to maintain nutrition and psychological health. For a crew of 500 people, toward the low end of genetic viability estimates, food production requires approximately 25,000 square meters of growing space. That's 2.5 hectares, compactly arranged through vertical farming techniques, but still adding mass, complexity, lighting power requirements, and failure modes to an already constrained system. What actual funding has produced, and what it reveals about the problem's scale? NASA's fiscal year 2024 budget ran to approximately $25 billion. The entire budget, not just interstellar research, covers every NASA program from Earth observation to the Artemis Moon program to the James Webb Space Telescope's continuing operations. The fraction dedicated to advanced propulsion research, which might someday contribute to interstellar capability, runs to tens of millions of dollars annually. Breakthrough Starshot, the privately funded initiative backed by Yuri Milner with an initial $100 million commitment in 2016, has produced valuable research into laser array technology, light sail materials, and miniaturized instrument packages. It has not produced a functioning prototype of anything approaching the full system. The laser array required, 100 gigawatts of focused power aimed at a precisely positioned target, doesn't exist anywhere in the world. The most powerful laser systems ever built peak at petawatt levels for femtosecond durations, not continuous gigawatt output. The Defense Advanced Research Projects Agency, DARPA, funded the 100-year Starship project starting in 2011, allocating $500,000 to seed an organization focused on the long-term challenge of interstellar flight. $500,000 for a project whose technical prerequisites would require expenditures in the trillions over decades. The contrast between the scale of funding and the scale of the problem creates a specific kind of cognitive dissonance. Serious people with serious credentials write serious papers about interstellar mission architectures. They present at conferences. They publish in peer-reviewed journals. The funding behind all of it combined doesn't approach the cost of a single large rocket launch. The Fermi paradox intersection, what it implies about interstellar travel more broadly. If interstellar travel were feasible on civilizational timescales, a few thousand to a few million years, the Milky Way galaxy should be colonized, or at least extensively explored, already. The galaxy is roughly 13 billion years old, a civilization achieving even modest interstellar capability, able to send probes or colonists to nearby stars over centuries, could colonize the entire galaxy in something like 10 to 100 million years, even without traveling faster than a few percent of light speed. 10 to 100 million years against a 13 billion year galactic age. A civilization that achieved interstellar flight a billion years ago could have colonized the galaxy 9 times over before Earth formed. Yet we see no evidence of colonization, no evidence of large-scale engineering of the galaxy, no signals from other technological civilizations, despite decades of SETI searches. The Fermi paradox has many proposed resolutions. One of the least appreciated: interstellar travel might simply be so difficult that even very advanced civilizations don't achieve it at galactic scales. The distances might be a genuine barrier even for physics that far surpasses ours. A civilization 10,000 years more technologically advanced might have fusion power, nanotechnology, artificial general intelligence, and capabilities we can't currently imagine, and still find interstellar travel beyond practical reach because the distances and energy requirements don't change with the level of technology. If the Fermi paradox resolution is interstellar travel is too hard for anyone, that doesn't mean it's impossible, only that the problem may be harder than even optimistic scenarios suggest, scaling with something more than just technological level. The psychological seduction of the problem. Something about interstellar travel captures human imagination in a way that makes sober analysis feel like betrayal. The nearest star, another sun, the possibility of worlds around it, the dream of the species as a spacefaring civilization, not trapped on one fragile world. That pull is real and not entirely irrational. Proxima Centauri hosts at least one planet in its habitable zone. The galaxy contains hundreds of billions of stars, and essentially every star appears to host planets. The probability that Earth contains the only life in the observable universe feels low, perhaps very low. The instinct that humanity shouldn't remain permanently confined to one world carries genuine weight. But the emotional pull of the dream doesn't change the physics. The distance to Proxima Centauri doesn't shrink because it matters to us. The energy required to send a crewed vessel there doesn't decrease because the journey would be historically significant. Carl Sagan described this tension better than almost anyone. In Pale Blue Dot, he wrote with genuine feeling about humanity's small place in the cosmos and the eventual necessity of moving beyond Earth. He also, throughout his career, maintained rigorous honesty about the difficulty of space travel at the scales the cosmos presents. The two positions aren't contradictory. One can simultaneously believe interstellar travel matters enormously as a long-term aspiration and accept that it faces barriers that may take centuries or millennia to overcome, if they can be overcome at all. The nearest star will still be there. The problem of reaching it won't become easier by underestimating it. What genuinely might change the picture and what wouldn't? Fusion power working at commercial scale, not experimental ignition, but sustained grid-scale energy production would be a significant step. It would provide energy sources orders of magnitude denser than chemical combustion and potentially scalable to propulsion applications. The path from commercial fusion power to fusion propulsion is long, but it exists in outline. Artificial general intelligence managing long-duration autonomous systems could eliminate the human crew requirement for the first missions, removing the biological and psychological barriers entirely. A robotic mission with AGI-level autonomy could navigate, conduct science, and make complex decisions over a century without requiring life support, genetic viability, or psychological stability. Radical life extension, biological or technological, would transform the human lifetime constraint. If humans could reliably live 300 years in good cognitive health, a century-long journey becomes a substantial, but not life-dominating commitment. Life extension research proceeds, but offers nothing near that scale within any credible near-term timeframe. What wouldn't change the picture? Faster computers, better materials science, absent a breakthrough in the specific domain of high-temperature, radiation-resistant materials.
incremental improvements in chemical propulsion, or better understanding of the destination through remote observation. The barriers are deep enough that incremental improvements don't move them. The honest answer to what would make interstellar travel possible is energy sources and propulsion mechanisms that operate on fundamentally different physics than what we currently use, combined with either radical biological modification of the crew, artificial general intelligence autonomous systems, or life extension that changes what human lifetime means. Each of these individually represents a transformative technology. Requiring all of them simultaneously for a crewed interstellar mission suggests the difficulty is compounding rather than linear. The stars themselves move. That complicates everything.
Proxima Centauri doesn't sit stationary at 4.24 light-years, waiting patiently for a spacecraft to arrive. Like every star in the galaxy, it orbits the galactic center and moves, relative to Earth, at roughly 22 kilometers per second across the line of sight. Over the timescale of any interstellar mission, decades to centuries, that motion accumulates into a substantial displacement. A spacecraft launched toward where Proxima Centauri appears today would need to aim not at the star's current position, but at where it will be when the spacecraft arrives. For a 100-year journey, the star moves roughly 70 billion kilometers from its apparent current position. That's approximately half an astronomical unit, comparable to the distance between Earth and the Sun. Navigation tables for the nearest stars have been calculated, and stellar proper motion is well understood. The correction is in principle straightforward, but it illustrates a broader point. Every assumption that seems simple at human scales becomes complex at interstellar scales. The target moves. The launching civilization changes. The spacecraft degrades. The communication lag grows. Nothing stays conveniently fixed. A mission plan that works on paper in 2050 may fail for reasons that are completely predictable from the physics, but that require decades of sustained engineering vigilance to manage. Managing those details over decades of silent flight, with communication delays growing from years to effectively irrelevant, requires autonomous systems maintaining mission parameters far longer than any autonomous system has ever been tested. The Oort cloud, the overlooked final exam before interstellar space. Most discussions of interstellar travel skip from the solar system to the interstellar medium as though the transition were clean and immediate. It isn't. The Oort cloud, the vast spherical shell of comets and small icy bodies surrounding the solar system, extends from roughly 2,000 to roughly 100,000 astronomical units from the Sun. The outer edge sits at roughly 1.6 light-years from Earth. An interstellar mission must traverse the Oort cloud before it exits the solar system. The cloud is not dense enough to pose a collision threat at most points, but its outer extent pushes into what might otherwise be called the near interstellar medium. Navigation through this region requires understanding a distribution of objects that has never been directly observed. The Oort cloud has been inferred from the behavior of long-period comets, but never imaged or catalogued. Voyager 1 won't reach the inner edge of the Oort cloud for another 300 years at its current speed. It won't complete passage through the cloud for roughly 30,000 years. The farthest any human-made object has ever traveled. Voyager 1, at about 223 astronomical units as of the mid-2020s, represents less than 0.5% of the distance to the cloud's outer edge, and less than 0.1% of the distance to Proxima Centauri. The sheer scale becomes comprehensible only when the numbers are laid out sequentially. Earth to Moon, approximately 1.3 light seconds. Earth to Mars, at closest approach, approximately 3 light minutes. Earth to Neptune, approximately 4 light hours. Earth to Voyager 1, approximately 20.6 light hours. Earth to the heliopause, roughly 18 light hours. Earth to the Oort cloud outer edge, roughly 1.6 light years.
Earth to Proxima Centauri, 4.24 light-years. Voyager 1, traveling for 47 years at a speed that seemed remarkable when it launched, hasn't made it to the Oort cloud yet.
It has covered roughly 20 light-hours in 47 years. The distance to Proxima Centauri in the same unit, 37,000 light-hours. The gap between current achievement and the destination isn't metaphorically large. It's literally larger than the gap between where humans were in 1977 and where they were in 2024, scaled by the transit time. The micrometeorite record from existing probes, what the data actually shows. Voyager 1 and 2, Pioneer 10 and 11, and New Horizons have all traveled through the outer solar system and into the interstellar medium, providing data on the actual particle environment at distances no previous instrument had reached. The Pioneer anomaly, an unexplained deceleration affecting both Pioneer probes that puzzled scientists for decades before being attributed in 2012 to anisotropic thermal radiation from the probes themselves, demonstrated that even simple objects behave unexpectedly at interstellar scales. New Horizons, carrying a student dust counter instrument, has provided the most detailed measurements of dust distribution in the outer solar system. The data shows dust density declining with distance from the Sun, reaching a minimum in the Kuiper Belt gap before a slight rise associated with the Kuiper Belt itself. The interstellar medium beyond the heliopause carries dust at densities higher than the near-interstellar gap, but lower than the inner solar system. What these missions haven't measured is the dust environment that a high-speed interstellar spacecraft would encounter. At the speeds the probes travel, up to about 17 kilometers per second for New Horizons, dust grains are essentially irrelevant hazards. At 4% of light speed, the same dust grains become hypervelocity impactors, carrying energies millions of times higher per particle. No instrument designed to measure dust at 17 kilometers per second is calibrated for 4% of light speed impacts. No material tested for resistance to hypervelocity impacts has been tested at interstellar speeds. The experimental database for designing an interstellar spacecraft hull doesn't exist. Every specification would need to be derived from first principles and models, then tested, somehow, at speeds that can't currently be generated anywhere on Earth or in space. The communication architecture that doesn't exist yet. Current deep space communication uses the Deep Space Network, a system of large radio telescopes at 3 locations around Earth, near Barstow, California, near Madrid, Spain, and near Canberra, Australia, that provide near-continuous coverage of missions throughout the solar system. The largest antennas span 70 meters across. The highest data rates achievable from planetary distances using radio frequency communication run to a few megabits per second. At Proxima Centauri distances, the inverse square law reduces received signal strength to essentially nothing with conventional radio. The signal from a spacecraft at 4.24 light-years using a transmitter comparable to the New Horizons spacecraft, roughly 12 watts, would arrive at Earth with a received power of about 10 to the minus 36 watts, far below the noise floor of any detector that exists or is physically plausible. Laser communication offers dramatically better directivity, concentrating energy in a much narrower beam, and significantly higher data rates at long distances. NASA has demonstrated laser communication from lunar distances with the LLCD, Lunar Laser Communication Demonstration, and from the Moon and Mars with more recent experiments. At interstellar distances, the laser beam spreads significantly, but still concentrates energy better than radio. A 1-meter aperture laser transmitter on a spacecraft, using a powerful enough laser, could potentially achieve detectable data rates at Proxima Centauri distances, but the pointing requirements become extreme. A beam aimed at Earth from 4.24 light-years must remain pointed at Earth, a moving target, with angular precision of roughly 1/10,000,000th of a degree. The spacecraft moves, vibrates, and rotates. Any misalignment dumps the signal into empty space. Active pointing systems can compensate, but they require knowing Earth's precise location to that accuracy, which requires prior knowledge of the interstellar distance, proper motion corrections for both the spacecraft and Earth, and real-time tracking information
that can only come from the signal being successfully received and acknowledged.
The pointing problem bootstraps itself in a way that requires a complete solution, not incremental improvements. The relativistic aberration problem, physics that changes what the stars look like. At significant fractions of light speed, the visual appearance of the sky undergoes relativistic aberration. Stars appear to shift toward the direction of motion. At 10% of light speed, stars ahead appear slightly compressed toward the forward direction, while stars behind spread slightly. At 50% of light speed, half the stars in the entire sky appear clustered into a forward cone, covering roughly 60 degrees around the direction of travel. The navigational implication: the star charts used for inertial navigation don't apply at relativistic speeds. The spacecraft needs to maintain navigation using a modified reference frame that accounts for aberration, and the algorithms for doing so need to be validated against real sky observations at speeds that have never been achieved. Beyond navigation, the spectral shifts are significant. Stars ahead of the spacecraft appear blue-shifted, their light shifted toward higher frequencies. At 10% of light speed, the blue shift runs about 5%, pushing ultraviolet emission into the deep ultraviolet. At 20% of light speed, Proxima Centauri's characteristic red emission shifts substantially toward shorter wavelengths. Instruments designed to observe the star at rest wavelengths would need recalibration or redesign for observation during the approach phase. The cosmic microwave background, the bath of low-energy photons permeating all of space, presents a specific challenge. At rest, the CMB appears isotropic at a temperature of 2.725 Kelvin, spread uniformly across the sky. At 10% of light speed, the forward hemisphere appears blue-shifted to higher energy, while the backward hemisphere appears red-shifted. The CMB ahead begins approaching microwave frequencies that could interact with spacecraft electronics in unexpected ways. At 20% of light speed, the forward CMB intensity becomes significant as a radiation source. The spacecraft experiences it as a beam of higher energy photons coming from directly ahead. This last point has a practical consequence rarely discussed. The CMB, entirely negligible as a radiation source at rest, becomes a meaningful photon flux directed at the forward face of a high-speed spacecraft. At 30% of light speed, the effective temperature of the CMB ahead rises to roughly 4 Kelvin, still cold, but measurably different. At higher speeds, it rises further. At 90% of light speed, the forward CMB appears at temperatures approaching visible light. At 99%, the forward CMB would appear as hot X-rays. A spacecraft accelerating toward Proxima Centauri at high fractions of light speed would be flying into an increasingly intense blue-shifted radiation environment that grows from negligible to dangerous purely as a function of speed. Even in perfectly empty space, with no interstellar gas or dust at all. The specific energy problem in numbers that resist being abstract. Human civilization currently consumes roughly 600 exajoules of energy per year, 6 times 10 to the 20th joules. That includes all electricity, transportation fuel, heating, industrial energy, and everything else. Accelerating a crude interstellar vessel of 100,000 kilograms to 4% of light speed requires roughly 2 times 10 to the 22nd joules, about 33 times humanity's entire annual energy consumption. Decelerating at the destination requires the same again. Total energy budget? 66 times current global annual energy consumption, just for the propulsion of a small, crude vessel. This assumes 100% efficient propulsion, 0 losses. Real propulsion systems operate at single-digit to tens of percent efficiency. A 10% efficient fusion drive would require 660 times current global annual energy consumption just for the propulsion. For a more realistic vessel mass of 1 million kilograms, 1,000 metric tons, a very modest estimate for a multi-decade crewed mission, the energy requirements scale by a factor of 10. 6,600 times current global annual energy consumption at 10% propulsion efficiency just for one mission. Current global energy production grows at roughly 2 to 3% per year. Compounding at that rate, humanity would reach the required annual energy output in roughly 3 to 4 centuries, if all of it were redirected to a single interstellar mission, which obviously can't happen. The energy problem isn't intractable on cosmic timescales, but it's deeply intractable on human civilization timescales. The materials science frontier, what the spacecraft would need to be made of, the leading face of an interstellar spacecraft traveling at several percent of light speed, encounters an environment with no analog in engineering experience. A combination of hypervelocity particle bombardment, high-energy cosmic rays, ultraviolet radiation, and, at high enough speeds, blue-shifted CMB photons creates a radiation and erosion environment that exceeds anything materials have been tested against. Known materials fail in specific ways at the relevant scales. Metals undergo radiation damage, knock-on displacement of atoms from crystal lattices, at rates that degrade structural properties over decades. Polymers break down under ionizing radiation. Ceramics fracture from thermal cycling and radiation-induced point defects. Diamond, often cited as a candidate for radiation-resistant materials in space applications, undergoes graphitization when exposed to high doses of ionizing radiation. New materials classes might perform better. Carbon nanotube composites, graphene laminates, boron nitride structures, each shows promise in specific regimes. None has been tested against the combination of conditions an interstellar spacecraft would encounter. None has been tested at the relevant particle energies, because generating those energies in a laboratory for duration testing would require a particle accelerator larger than any that exists. The materials science of an interstellar spacecraft can't be developed through normal engineering iteration. Build, test, find failure modes, improve. The test conditions can't be replicated on Earth. The failure modes can't be identified until a spacecraft actually experiences the environment. But no one will commit to building a real spacecraft until the materials science questions are answered. This circular dependency, can't test materials without a spacecraft, can't build a spacecraft without tested materials, represents one of the more intractable development loops in the entire problem space. The asteroid mining prerequisite. What has to happen before interstellar propellant becomes available? Any propulsion system capable of interstellar flight needs either propellant of extraordinary energy density or propellant produced along the way. For fusion-propelled missions, helium-3 from outer solar system sources represents the most commonly cited fuel. Accessing that helium-3 requires an industrial presence in the outer solar system that doesn't currently exist and has no funded development path. Asteroid mining of the inner solar system, the asteroid belt between Mars and Jupiter, remains in its commercial infancy as of the mid-2020s. Several companies attempted to develop asteroid mining technology in the 2010s. Most failed or pivoted. Planetary Resources was acquired by Consensus in 2018 and effectively shuttered. Deep Space Industries was acquired by Bradford Space in 2019. The industry hasn't produced a single commerciially extracted kilogram of asteroid material. For outer solar system resource extraction, Jovian atmosphere mining, Saturnian ring material, Oort cloud objects, the required technology doesn't exist at any level of development. No spacecraft has ever conducted sustained operations in the Jovian atmosphere. No spacecraft has ever extracted material from a gas giant. No robotic system capable of operating autonomously for decades in deep space without ground control has been demonstrated. The prerequisite chain for an interstellar mission includes commercial space mining becoming viable, expansion of mining operations to the asteroid belt, development of robotic deep space operations, extension of mining to the outer solar system, decades of helium-3 extraction from gas giant atmospheres, transport of extracted fuel to a construction facility, construction of the interstellar vessel itself. Each step takes decades in even optimistic projections. The steps are sequential. Each requires the previous one to be completed first. The question of what we're actually asking when we ask, can humans reach the nearest star? The question has at least three distinct interpretations, and they have different answers. Can a biological human, born and raised on Earth, travel to the Proxima Centauri system and return within their natural lifespan? Almost certainly not within any foreseeable future. The energy requirements, the journey duration, the radiation environment, and the lack of deceleration capability at the destination make it implausible on human lifespan timescales without either radical life extension or physics that doesn't exist. Can a vessel carrying humans, including descendants of the original crew, reach the Proxima Centauri system and establish some form of presence there? Possibly, on timescales of centuries to millennia, given energy and propulsion breakthroughs and solutions to the genetic, psychological, and engineering challenges described throughout this text. The word possibly carries significant weight here. Can something recognizably derived from human civilization, either biological humans modified beyond current recognition, or artificial intelligences created by humans, or some hybrid, reach the Proxima Centauri system? On sufficiently long timescales, probably yes, if civilization survives and continues developing. The distances are real but not infinite. The laws of physics permit travel at sublight speeds. The barriers are engineering, not physics. These three interpretations produce answers ranging from almost certainly not to probably eventually. The question's framing determines which answer seems appropriate. When most people ask whether humans can reach the nearest star, they have the first interpretation in mind: a human in a spacecraft departing within a plausible human institutional time frame, arriving within a span meaningful to the people who launched the mission. By that interpretation, the honest answer is no, not with anything currently understood or under development, and not within any time frame that matters to anyone alive. The second and third interpretations open up longer timescales and more radical transformations of what human and reach mean. Those interpretations may carry valid answers, eventually, but they require civilization persistence, technological development, and perhaps biological or technological transformation that pushes the question outside the frame of anything currently predictable. The most overlooked barrier to interstellar flight might not be energy or distance. It might be the human nervous system itself. Humans evolved for a specific set of environmental conditions over roughly 300,000 years of anatomical modernity and millions more of cognitive evolution in hominid ancestors. Those conditions include gravity of approximately 9.8 meters per second squared, atmospheric pressure of roughly 101 kilopascals at sea level, a day-night cycle of 24 hours governed by solar light, radiation doses orders of magnitude lower than the interstellar environment, access to a planetary surface, and interaction with hundreds to thousands of other individuals across a lifetime. Strip away all of those conditions simultaneously, and you don't just create engineering problems, you create a mismatch between the human organism and its operating environment that extends down to neurobiology. The human brain evolved to process a richly varying sensory environment, changing light, changing weather, the textures of soil and wind and rain, the visual complexity of natural landscapes, the social complexity of a tribal group embedded in a larger community. What happens when that stimulation disappears for decades? Sensory deprivation research dating to the 1950s, conducted initially by John Lilly and Donald Hebb at McGill University, established that humans deprived of normal sensory input deteriorate cognitively and psychologically within hours to days. The isolation tanks of the 1980s, used for short-duration meditation and therapy, operate on the edge of what the brain tolerates. The difference between a 90-minute float tank session and a century-long interstellar voyage is roughly 50 million to 1. The brain doesn't just function suboptimally in sensory-limited environments. It generates experiences to compensate: hallucinations in extended isolation,
confabulation, the construction of social worlds where none exist. Long-duration isolation reliably produces distortions in time perception, disruptions in memory consolidation, and changes in personality that partially persist after isolation ends.
The mechanisms involve actual changes in neuroplasticity, the brain restructuring itself in response to its environment, which is exactly what it should do, but not in ways optimized for mission performance. The decision architecture problem: who commands what and when? Every space mission flown by any agency has operated under a clear authority structure. Mission control on the ground maintains operational authority. Crew exercises delegated authority for time-critical local decisions. When ambiguity arises, the crew communicates with ground deliberates, and instructions return. This works because communication delays between Earth and crewed spacecraft have never exceeded about 40 minutes round trip, even for Mars mission planning scenarios. At 4 light-years, round-trip communication delay reaches 8.48 years. A crew member experiencing a medical emergency can't wait 8 years for a response. A navigation hazard detected on approach to Proxima Centauri requires immediate response, not a response planned from Earth 8 years after the hazard was reported. Every time-sensitive decision during the entire mission, and time sensitivity in spaceflight often means seconds to hours, not years, must be made autonomously by the crew or by onboard systems. This fundamentally transforms the crew's role. Rather than operators executing a mission plan developed and supervised by thousands of ground-based experts, they become fully independent decision-makers for a decade-long, minimum, or century-long series of novel situations with no external consultation possible. The crew must contain, collectively, the expertise of every specialist who would normally be available through ground support: physicians, engineers, geologists, biologists, psychologists, computer scientists, physicists, chemists, and whoever else the mission might require. No group of humans has ever needed to be simultaneously expert in all domains required to keep themselves alive and their mission productive, without access to any external expertise, for durations exceeding a year. The combination of expert breadth and isolation duration has no historical precedent. Training programs, artificial intelligence support systems, and onboard libraries can help, but they can't replicate the adaptive expertise of thousands of specialists applying contemporary knowledge to novel problems in real time. The embryo option and its uncomfortable implications. A proposal that appears occasionally in serious engineering literature involves launching not adult humans, but frozen human embryos, managed by artificial systems, with a plan to gestate and raise children near the destination. The embryos would travel the entire interstellar distance as essentially inert cargo, avoiding the psychological and physiological problems of decades in space. Artificial wombs would gestate the children. Robotic systems would raise and educate them. The proposal solves several technical problems. No crew means no life support for the journey, no psychological deterioration, no genetic bottleneck from reproducing in transit, and no need for the kind of political continuity that would sustain a multi-generational human crew. But it creates problems of a different kind. Children raised by robots in an isolated spacecraft would have no human models for human behavior, no human culture passed down through lived experience, no models for human relationships, human judgment, human ethical reasoning. Whatever they became would be shaped entirely by whatever content humans managed to encode in advance: books, videos, simulations, AI trainers, without the lived human context in which those materials were created. Whether the beings produced by that process would be human in any meaningful sense is genuinely uncertain. They would be biologically human. They would have human DNA and human neurological architecture. But the content of that architecture, the person, emerges from developmental experience, social environment, and cultural transmission that would be entirely artificial. The ethical questions around deliberately creating children for a specific purpose, interstellar exploration, who could never consent to the conditions of their existence, and who would have no alternative to whatever life the mission imposed on them, have no resolution in any current ethical framework. They represent a category of moral problem that human civilization has never previously confronted at scale. The solar sail revival, what's actually being built and why it matters. Breakthrough Starshot, announced in 2016, proposed accelerating gram-scale light sails to 20% of light speed using a ground-based laser array. But long before Starshot, solar sails operating on sunlight rather than lasers had been demonstrated. The Japanese Icaros mission in 2010 deployed a 14-meter square sail and used solar photon pressure for both propulsion and attitude control during an interplanetary trajectory to Venus. NASA's NanoSail D2 mission in 2011 demonstrated solar sail deployment in low Earth orbit. The Planetary Society's LightSail 2 mission, launched in 2019, successfully demonstrated controlled solar sailing, using the sail to change orbital altitude through radiation pressure in low Earth orbit. LightSail 2 operated until November 2022, when atmospheric drag caused re-entry. These missions proved the concept works. Photon pressure from sunlight can propel a spacecraft, and the sail can be steered by adjusting orientation. But the numbers for interstellar applications remain prohibitive. Sunlight intensity falls with the square of distance from the Sun. At Jupiter's orbit, sunlight provides roughly 27 times less photon pressure than at Earth's orbit. Beyond the heliosphere, solar photon pressure becomes negligible. Solar sails can reach useful speeds in the inner solar system. Estimates for optimal solar sail trajectories suggest achieving roughly 1 to 3% of light speed with sails of sufficient size and low enough mass, using close solar passes to maximize acceleration. 1 to 3% of light speed gets you to Proxima Centauri in roughly 140 to 420 years. A genuine interstellar mission timescale, if you're willing to accept that the crew would have to survive an extraordinary duration. The sail technology required for the higher end of that performance doesn't exist yet. A sail capable of surviving a close solar pass within 15 to 20 solar radii must withstand intense ultraviolet and X-ray radiation, heat loads in the hundreds of kilowatts per square meter, and corpuscular bombardment from the solar corona, all while maintaining structural integrity for continued photon capture. Carbon fiber composites and thin film aluminum have been proposed. None has been tested at those conditions. The magnetic braking concept, stopping at the destination, if a spacecraft reaches Proxima Centauri at even a small fraction of light speed, decelerating to orbital or landing velocities requires enormous energy. Carrying deceleration propellant from Earth roughly doubles the fuel mass requirements, already prohibitive. But the Proxima Centauri system itself might provide a braking mechanism. Proxima Centauri emits a stellar wind, a stream of charged particles from its atmosphere, more intensely than the Sun due to its frequent flares and active corona. A spacecraft equipped with a sufficiently large magnetic sail, a mag sail, could use the magnetic pressure of this stellar wind to decelerate upon arrival. The concept was proposed by Robert Zubrin and Dana Andrews in 1991. The mag sail generates a magnetic field that acts as a drag against the stellar wind, converting the spacecraft's kinetic energy into waste heat and slowing it. No propellant required at the destination, just an electromagnetic system generating a large-scale field. The engineering challenges. The magnetic coil required to generate an effective mag sail for deceleration from several percent of light speed would need to span tens to hundreds of kilometers across. A thin, superconducting wire loop of that size, maintaining superconductivity over decades of flight, and then generating the required field upon arrival, represents a manufacturing and materials challenge with no current solution. The current required to generate the field would be enormous. The mechanical structure to keep the loop deployed in the absence of gravity requires tension and geometry that haven't been worked out. Mag-scale decelerations have been modeled theoretically, and the concept appears physically valid. Nothing resembling a demonstration has been built or tested, even at laboratory scale. The sterilization problem. Interstellar quarantine in reverse. When a spacecraft from Earth arrives at a planetary system that might host life, and Proxima b sits in a potential habitable zone, it carries Earth's microbial contamination. Despite best efforts at sterilization before launch, spacecraft historically carry hundreds to thousands of viable microorganisms. The Viking landers in 1976 were among the most carefully sterilized spacecraft ever built, heat-treated to kill surface contamination, and even they likely carried some viable organisms in interior spaces.
For Mars, the Planetary Protection Protocols of COSPAR, the Committee on Space Research, set requirements for bioburden on spacecraft visiting potentially habitable environments. Implementing those protocols adds cost and constrains mission design. Violating them means potentially contaminating the only other environment in the solar system where life might exist with Earth biology, making it impossible to determine, in hindsight, whether any life found there was indigenous or introduced. For an interstellar mission to Proxima b, which might host life, the sterilization challenge scales dramatically. A crewed spacecraft can never achieve sterilization. Humans shed billions of microorganisms per hour through skin flaking, breathing, and waste. Any habitat containing living humans necessarily contains Earth's microbial ecosystem. The implications split in two uncomfortable directions. Either the crew must never contact the planetary environment, conducting all science remotely or through sterilized robotic systems, while never actually setting foot on the planet they traveled 4 light-years to reach. Or contact with the planet means irreversible biological contamination of a potentially life-bearing world. The contamination can't be undone. If indigenous life exists and interacts with Earth microbes, the consequences range from competitive exclusion of native life to ecosystem disruption to, in the most dramatic scenario, pathogens spreading between two entirely separate evolutionary lineages with no shared immune history. The sterilization problem and the quarantine problem have no good answers. They represent genuine ethical constraints on mission design that haven't been resolved, even for the relatively simple case of robotic missions to Mars. The communication time capsule, what gets sent back and to whom.
A crewed interstellar mission would generate scientific data of enormous value. Observations of a stellar system from within, geological and biological data from a nearby planet, in situ measurements of the interstellar medium. Getting that data back to Earth matters enormously, but the communication delay transforms data transmission into something more like a time capsule than a report. A crew member observing Proxima b's surface sends a description. It arrives at Earth 4 years and 3 months later. The scientists who designed the observation protocol may have retired or died. The research questions that motivated the observation may have been superseded by subsequent discoveries. The data arrives into an intellectual context different from the one that generated the questions it was meant to answer. Over a sufficiently long mission, this lag becomes culturally significant. The civilization that launched the mission in 2050 and receives data from the destination in 2015-5 has changed in ways comparable to the changes between 1900 and 2005. The scientists analyzing the data are not the descendants of the original mission team in any meaningful professional or cultural sense. The questions they'd want answered are not the questions the mission was designed to address. This creates a curious reversal. The most valuable data might be what the crew observes serendipitously, things no one anticipated, rather than what the original mission designers planned to measure. But serendipitous observation requires scientific judgment, and exercising that judgment with an 8-year communication lag for consultation means the crew must make scientific priority decisions entirely autonomously. Planning for a century-scale mission requires anticipating which scientific questions will still matter a century from now.
Some will, fundamental chemistry, geology,
atmospheric physics don't change in their relevance. Others would have been answered by intervening technological development. Some questions we'd desperately want answered don't exist yet as concepts because the frameworks for asking them haven't been developed. How do you plan an observation protocol for questions you don't know how to ask? The trajectory planning problem at a scale that requires new mathematics. Mission planning for a flight to Mars uses well-understood orbital mechanics, with trajectories calculable using Newton's laws, plus relativistic corrections that are small but known. The spacecraft's path can be planned years in advance and adjusted continuously through ground control. Interstellar trajectories require accounting for effects that don't significantly affect inner solar system missions. The gravitational influence of passing stars, even at interstellar distances, close stellar passages create perturbations. The Sun passes within 3 light-years of other stars roughly once per 80,000 years. Over a century-long mission, the gravitational field through which the spacecraft moves includes contributions from dozens of neighboring stars at distances that vary over the mission timeline. High-precision trajectory calculation for an interstellar mission requires knowing the masses and positions of all neighboring stars to sufficient precision. The Hipparcos and Gaia satellite programs have mapped stellar positions with unprecedented accuracy, but the precision needed for century-scale trajectory planning exceeds even Gaia's capabilities. Small errors in stellar mass or position estimates, propagated over decades of gravitational influence, could accumulate into trajectory errors of astronomical unit scale. At higher fractions of light speed, general relativistic effects on the trajectory become non-negligible. The spacecraft's own gravity is negligible, but the warping of space-time by the Sun, by Proxima Centauri, and by intervening mass distributions affects the path at a level that matters for precision navigation. These calculations exist mathematically, but have never been validated against real spacecraft behavior at the relevant speeds, because no spacecraft has ever traveled at a fraction of a percent of light speed, let alone the few percent relevant for interstellar missions. The three-body problem of interstellar missions, Proxima Centauri isn't alone. Proxima Centauri belongs to a triple-star system. Alpha Centauri A and B form a binary pair, 2 stars roughly the size of the Sun orbiting each other at a separation averaging about 23 astronomical units, slightly larger than the distance from the Sun to Uranus. Proxima Centauri orbits the Alpha Centauri binary at a distance of roughly 13,000 astronomical units, about a fifth of a light-year, on an orbital period that may be in the millions of years. Whether Proxima actually orbits the binary in a bound orbit or merely passes through the neighborhood remains uncertain. If bound, the orbital eccentricity must be quite large. Either way, when an interstellar spacecraft arrives at the Proxima Centauri system, it enters a gravitational environment significantly more complex than the solar system. A red dwarf primary, 2 much brighter G-type stars at roughly 2,000 astronomical units, and the gravitational perturbations all 3 impose on any orbit around Proxima. Proxima b, in the habitable zone of Proxima Centauri, orbits at roughly 0.05 astronomical units from its star, about 1/20th the Earth-Sun distance. At that proximity to Proxima, the planet experiences intense tidal forces that almost certainly produce tidal locking. But it also sits within a system where Alpha Centauri A and B are bright enough to be significant light sources, not sufficient for photosynthesis, but bright enough to produce a permanently lit night sky on Proxima b. Any spacecraft attempting to establish orbit around Proxima b must navigate the combined gravitational influences of Proxima Centauri, the 2 Alpha Centauri stars, and Proxima b itself. The orbital mechanics are calculable but complex, requiring careful planning to avoid unstable orbital trajectories. More importantly, any robotic lander on Proxima b must be designed for the specific gravitational and thermal environment of a tidally locked world orbiting a flare star, an environment with no solar system analog, for which no engineering heritage exists. The social legacy problem, what happens to the people left behind, A crewed interstellar mission doesn't only transform the people on board, it creates an entirely new category of human relationship on Earth: the families and communities of people who left and cannot return. The crew's children, born after launch, will never know their parents. Their parents' parents will die waiting for signals that take 4 years to arrive. When those signals do arrive, they describe people who have aged differently than Earth's passage of time, or who have died, and who exist in a context completely unlike Earth's. The connection between crew and Earth community becomes increasingly attenuated with each passing decade. The political and psychological dynamics of this relationship have no precedent. Close analogies, Antarctic expeditions, submarine patrols, overseas military deployments, all involve the possibility of return within months to years. The families of interstellar crew members would need to sustain connection with people who will never return, who will age and die in transit, and whose communication arrives as artifacts of a past that has no present relevance. Human cultures have structures for handling permanent absence, death, emigration to inaccessible places, disappearance. But those structures assume finality. The families of interstellar crew members would receive ongoing communication, a 4-year delayed window into the lives of people permanently and voluntarily separated, without the closure of finality. Whatever psychological structures exist for that kind of relationship would have to be invented. The mission's social impact extends further. A civilization that launches a crewed interstellar mission has made a statement about values, priorities, and its vision of the future. That statement propagates through culture. Whether the statement is inspiring or alienating depends on who's asking and what sacrifices the mission required of the population that didn't go. Interstellar missions don't just challenge the people who travel, they challenge the conception of community, obligation, and shared purpose of the civilization that launches them. A few final observations before the honest accounting. The history of human exploration contains no precedent for what interstellar travel would require, not in scale, not in duration, not in isolation, not in the nature of the commitment. The voyages of Magellan's circumnavigation took 3 years and required 37 men with 1 ship to complete. Magellan himself died en route. The Apollo program consumed roughly 4% of the US federal budget at its peak, employed 400,000 people, and achieved its goal in 8 years. The Manhattan Project, the other canonical example of civilizational-scale technological commitment, employed over 130,000 people at its peak and produced operational weapons in under 4 years from initial funding. Each of those achievements involved extraordinary mobilization. Each also operated within an environment where the goal was technically achievable with existing physics and rapidly improvable engineering. The barriers were money, will, and iteration time, not the laws of thermodynamics. Interstellar travel faces barriers in a different category. The distances are not a matter of will or funding. The radiation environment doesn't negotiate. The rocket equation doesn't soften for human ambition. These aren't barriers that dissolve when enough people care enough. They're constraints imposed by the universe's structure, and acknowledging them clearly isn't pessimism. It's a prerequisite for thinking honestly about what would actually be required. The honest accounting, 3 categories. Firmly established by physics, engineering, and biology is the following. The distance to Proxima Centauri, 4.24 light-years, or roughly 40 trillion kilometers, represents approximately 10,000 times the distance New Horizons has traveled in 47 years of flight. No propulsion system currently operational or in funded development could reduce a transit time below tens of thousands of years. Reaching Proxima Centauri in a century would require sustained velocities of approximately 4% of light speed. Accelerating 1,000 kilograms to 4% of light speed requires roughly 2 × 10⁻17 joules, approximately 5 million times the energy of the Hiroshima bomb. Decelerating at the destination requires comparable energy again. The Tsiolkovsky rocket equation makes chemical and even nuclear thermal propulsion physically inadequate at interstellar scales. The required mass ratios exceed the mass of the observable universe long before achieving the necessary velocities. Galactic cosmic rays at interstellar cruise velocities deliver radiation doses far exceeding current career limits for astronauts, and no shielding solution exists that provides adequate protection at acceptable mass. Microgravity exposure over decades produces cumulative physiological degradation, bone density loss, cardiovascular deconditioning, spaceflight-associated neuro-ocular syndrome that worsens beyond the already significant effects documented in year-long ISS missions. Communication round-trip delay at Proxima Centauri distances reaches 8.48 years, eliminating ground support for any time-critical decision during the mission. Interstellar dust and gas, negligible hazards at solar system speeds, become hypervelocity impactors at several percent of light speed, delivering per-impact energies comparable to rifle rounds for sub-microgram grains. No material has been tested against these impact conditions, and generating the test environment requires particle accelerators beyond any that exist. Actively debated and unresolved is the following: whether laser-driven light sails on the breakthrough Starshot model can achieve 20% of light speed for gram-scale probes remains an open engineering question. The laser array required doesn't exist, the sail materials haven't been tested at the required thermal loads, and the pointing precision needed has never been demonstrated. Whether fusion propulsion, given a functioning commercial fusion reactor as a starting point, could achieve the exhaust velocities needed for practical interstellar missions within 3 to 4 centuries of development. Whether magnetic braking using stellar wind at the destination could provide practical deceleration without carrying return propellant. The concept appears physically valid, but no component has been demonstrated at laboratory scale. Whether generational ship missions carrying populations of several hundred to several thousand people could maintain genetic viability, psychological stability, and functional governance over a century-scale transit. The relevant fields of population genetics, long-duration space psychology, and closed-system life support each identify serious challenges, but none rules the mission out in principle. Whether advanced artificial intelligence systems, sufficiently capable to manage autonomous decision-making for decade-scale missions, could substitute for ground support and reduce crew expertise requirements. The required capability level significantly exceeds current AI systems and has no clear development timeline. Whether the sterilization and planetary protection challenges around a potentially inhabited Proxima b could be resolved to scientific and ethical satisfaction before mission design is finalized. Genuinely beyond current understanding is the following: whether any propulsion concept operating within known physics, fusion, antimatter, laser sail, solar sail, can realistically scale to crewed interstellar missions on any human civilization timescale, given compounding energy, mass, and infrastructure requirements. Whether the human organism, with or without biological or technological modification, can maintain physical and psychological integrity for the durations required by any plausible interstellar transit. Whether the political, economic, and institutional continuity required to plan, fund, build, launch, and sustain an interstellar mission over a century or more falls within the capacity of any human institutional form that has ever existed or can be plausibly imagined. Whether exotic propulsion concepts, Alcubierre warp drives requiring negative energy density, traversable wormholes requiring exotic matter, Mach effect thrusters whose physical basis remains contested, have any relationship to physical reality or represent mathematical artifacts without operational meaning. Whether the destination, Proxima b, has an atmosphere, liquid water, or any condition that would justify a crewed mission over the robotic alternative, given that its habitability remains uncertain from remote observation. And most starkly, whether the gap between what interstellar travel requires and what human civilization can provide will ever close, or whether the distances between stars represent a permanent feature of the universe that intelligent life simply must accept.
The nearest star sits at 4.24 light-years.
Every object humans have ever built moves at less than 1,000th of 1% of the speed needed to reach it within a lifetime. The physics hasn't changed. The distance hasn't changed. What changes, slowly and without guarantee, is human capability. Whether that capability will ever reach the scale the problem requires, that question has no honest answer available from inside human civilization in the mid-21st century.